Chapter 3, Section 3, Increasing and Decreasing Functions, and the First Derivative Test. All right, we can use derivative to determine relative extrema and figure out whether they're relative maximums from relative minimums. But before we can get to that, that's the first derivative test, we have to talk a little bit about the idea of increasing and decreasing functions. Now, as the name might indicate, an increasing and decreasing function kind of based on the way the graph of the function is sketched. If you go from left to right and your graph is rising, we consider that increasing. If it's dropping or falling, we consider that decreasing. But in terms of a little bit more mathematical way of saying it, we have the following definition. A function f is increasing on an interval if for any two numbers x sub 1 and x sub 2 in the interval, and if x sub 1 is less than x sub 2, this implies that f of x sub 1 is less than f of x sub 2. So what that is saying here is, if you're looking at these values going from left to right, notice from left to right that the y value is bigger than the y value on the left here. So my graph is rising or increasing. A function is decreasing on an interval if for any two numbers, x sub 1 and x sub 2 on the interval, where again x sub 1 is less than x sub 2, this implies that f of x sub 1 is greater than f of x sub 2, which means that the values are getting smaller on the right and that your graph is decreasing. Okay? So, as I try to simplify it here a little bit, simply, a function is increasing if as x moves to the right, the graph moves upward, and a function is decreasing if x moves to the right, the graph moves downward. In the red, I have it going downward. This is decreasing. F prime of x is less than 0. Now, f prime of x is less than 0. What does that mean? It means that the slopes of the tangent lines are negative. And if you try to draw a tangent line here to this curve, you can see it's going to have negative slope. Over here, this is kind of a brown color here. This is increasing. F prime of x is greater than 0 because, again, if I try to draw a tangent line to this curve at any point on this curve, it's going up and to the right. The slope is positive. But down here in green, in between the two, I have a horizontal line, so we don't say that the graph is increasing or decreasing. We say that the graph is constant, which means that we would have a horizontal tangent line because it's a horizontal line itself. F prime of x is equal to 0. Now, with that stated, we can determine where it's increasing and decreasing by taking the derivative. Theorem, the test for increasing and decreasing functions. Let f be a function that is continuous on the closed interval from a to b and differentiable on the open interval from a to b. If f prime of x is greater than 0, if f prime of x is greater than 0 for all x in the interval from a to b, then we say that f is increasing on the closed interval from a to b. If f prime of x is less than 0 for all x in a, b, then we say f is decreasing on the closed interval from a to b. And f prime of x is equal to 0 for all x in the open interval a, b, then we say f is constant for the closed interval a, b. So increasing, decreasing, constant. Yeah, you're going to have to keep track of that, and we can by taking the derivative. So what I'm going to show you here is how we go about to determine the intervals, and I'm going to write open intervals. I know that these are closed, but I'm going to write open intervals for which my function f of x equals x to the third minus 12x is increasing and decreasing. Now, f is a continuous function because it's a polynomial function. If I take the derivative, f prime of x would be 3x squared minus 12. Now, the textbook shows this work a little bit different, but I think you're better off if you kind of follow the way I write this out. So I've taken the derivative, and now I'm going to set the derivative equal to 0. What is that going to give me? It's going to give me critical numbers. It's also going to give me where the derivative is equal to 0, right? Where it's equal to 0, so it might give us like a constant value. But you have to think about it. If a function's increasing and then it's decreasing, boom, up there, the slope is going to be equal to 0. So I need to know those critical numbers. So I solve this by factoring. It's always nice when it factors. And I get two critical numbers here. I get x equal 2 and negative 2. So here's where I draw a number line. And I draw my number line. This is going to be f, for the function f, this is going to be f prime, its derivative. Okay, I'm going to put my two critical numbers down. My two critical numbers are 2 and -2. Then I'm going to pick a test point from each of the three subintervals, and I'm going to plug it, because it's f prime, that's why I labeled it, I'm going to plug it in to the derivative. I can plug it into this form. It's more convenient at times. So I take a number from here, any number that's smaller than -2, like let's say -10. 3 times, plug -10 in here, -10 minus 2, that's negative, -10 plus 2, that's negative. I have a positive times a negative times a negative, that's positive. So I'm going to put a little plus sign to remind me that that's positive. Then I take a value from in here, pick something simple, like 0. 3, that's positive, times 0 minus 2 is negative, times 0 plus 2 is positive, so I have positive times positive, that's going to be a negative. And then I take a value from here, let's say 10. 3, 10 minus 2 is positive, 10 plus 2 is positive, positive times positive times positive is positive. Now, I know it's only one example, and you may be looking at this and saying, oh, I bet it always alternates. Well, on a lot of them, but not all of them. It doesn't have to alternate. It kind of depends on how many factors you have that give you that critical number. So in this case, I have positive, negative, positive. Now, what does positive tell me? Positive tells me that it's increasing. So I put a little arrow that's going up and to the right to show me that it's increasing. Negative tells me it's decreasing. Negative. So I put an arrow like this. Positive tells me it's increasing. Now it says write open intervals to tell you where it's increasing or it's decreasing. Well, it's increasing, and I didn't give myself enough space there again. Here, from -infinity to -2, whoops, -2, and from 2 to infinity. So union from 2 to infinity. Okay, it's decreasing. I like to abbreviate when I do this work, but I would suggest that you don't abbreviate a whole bunch of things on the AP test because they might not understand what you're trying to indicate. But it's negative here from -2 to +2. Okay. Now I also want you to kind of think about this as far as, notice increasing to decreasing. It's going to peak up here. I'm going to have a relative maximum. From decreasing to increasing, it's going to bottom out. I'm going to have a relative minimum. Increasing and decreasing are going to lead us to be able to determine whether we have relative extreme that are maximums or relative extreme that are minimums. Okay, but before we get there, I'm kind of jumping the gun, a little bit of a tease there. Let's check out these guidelines. All right, the guidelines for finding intervals for which a function is increasing or decreasing. Let f be continuous on the open interval AB. To find the open intervals for which f is increasing or decreasing, find those critical numbers. Use those critical numbers to set up test intervals. That's why I drew out the number line. Determine the sign of f prime at one test value in each of the intervals. That's what I was doing before. I plugged in numbers to see if it was positive or negative. And then, of course, we're going to use the theorem, which is the test for increasing and decreasing, to determine whether that means they're increasing or decreasing, whether they're positive or whether they're negative. Okay? Now, I can use this not just on an open interval AB. Whoops. I guess it would help if I could point to it. Not just on an open interval AB, but I can do this on all real numbers, or all numbers smaller than b, all numbers greater than a. Other types of intervals, you know, the infinite intervals. A function is strictly, there we go. I should try to figure out how do you say that word, because I say it monotonic, but I'll bet you a quarter. Let's see if I can find it here real quick. You guys will hang in there for just a second. Let's pronounce monotonic. Now, here we go. Let's see how we do this. Listen close. Oh, probably some commercial here.
Monotonic. Monotonic.
Oh, I've been saying monotonic at times. Monotonic. 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 Okay. A function is strictly monotonic. Like my voice is monotonous at times. It's at one tone all the way through. A function is strictly monotonic on an interval if it is either always increasing on the entire interval or if it's decreasing on the entire interval. All right? For example, this guy right here. This guy right here, f of x equals x to the third. If I take the derivative, well, there's the last function being processed, I get 3x squared. If I set my derivative equal to 0 to find my critical numbers, I get x equals 0. If I draw out my number line, following all the guidelines here, following all these guidelines here, if I draw out my number line here for f prime, put 0 down and test it, take a number from, let's say over here, -1. Plug -1 into the derivative, I get positive. Take a number over here like +1, take +1, plug it in, positive. This thing is increasing, this thing is increasing, this thing is strictly monotonic. It is increasing for all values, so increasing from -infinity to infinity. Here's an example of a function that is strictly monotonic. Now this function here kind of looks like it's also strictly monotonic because it appears to be going up and to the right, but there is an open interval, or there is an interval of values here, let's say from A to B, where it's constant. So this is not strictly monotonic because it's not increasing or decreasing on this entire interval. Now you say, well, what about back here at 0? Wasn't the derivative at 0? Yeah, for a finite number of points, not for an infinite number of points. Okay, that it works. So this is not strictly, if I can write it, monotonic. All right, now, finally, this is such a good theorem that's coming up here, and we're going to use this one to death. The first derivative test. Now, it's called the first derivative test because it involves the first derivative. When we talk about second derivatives and the second derivative test, which just happens to be the second one that we talk about, it's not because it's the second one we talk about, it's because it's going to use the second derivative. But in this case, the first derivative test, which is the first one we talk about, does involve the first derivative, so it's kind of ironic that way. Let C be a critical number on a function f that is continuous on an open interval I containing C. So C is a critical number, continuous function. If f is differentiable on that interval, except possibly at C itself, then f of C can be classified as follows. If f prime of C changes from negative to positive, let's go back here. Okay, from negative to positive. See how it's going downward? Then it's going upward, from left to right there. Then f of C is a relative minimum. From negative to positive, a relative minimum of our function f. If f prime of x changes from positive to negative, the other order, let's go back to my drawing here. From positive to negative, notice up here, then f of C is a relative maximum. So I don't need a sketch. I can just use this first derivative test to determine if I have relative extrema at my critical numbers. If f prime of x, does not change sign at C, then f of C is neither a relative min nor is it a relative max. Okay? So if it does not change signs, it's neither. All right, now let's try some examples. Find the relative extremum of a function f of x equals 1/2 x minus the cosine of x on the interval of the open interval from 0 to 2 pi. Now this is a continuous function. Okay, I'm going to take the derivative. By the way, if you're wondering, well, you just stated right out there that it's a continuous function. This is linear. This is a trig function. Okay, we know this is continuous. We know this guy's continuous. Their sums or differences are going to be continuous. We had that back in the section on continuity. F prime of x is equal to, taking the derivative, 1/2 plus the sine of x. Remember, the derivative of cosine of x is negative sine x, so minus a negative. So I take 1/2 plus the sine of x, set it equal to 0. Okay, I'm going to get, now remember, I don't want all values because there's infinitely many values here because I am keeping it here on 0 to 2 pi. So I have negative 1/2 at 7 pi over 6 and at 11 pi over 6. I draw my number line. Here's 0, here's 2 pi. So 7 pi over 6 might be about here, and 11 pi over 6 might be about here, approximately. So I have 1, 2, 3 intervals. I'm going to take a value from here, like pi. I'm going to plug, this is for f prime. Always label. If I plug in pi, the sign of pi is 0. 1/2 plus 0 is 1/2, which is positive. Increasing. Take a value in here like 3 pi over 2. The sign of 3 pi over 2, if I plug in for x here into my derivative, is negative 1. 1/2 plus negative 1 is negative 1/2. Decreasing. Now, what happens here, now I don't have a nice specific one. I mean, I could plug in 6.28, which is a little bit smaller than 2 pi. I could plug that into here and get my calculator out. Where's my calculator when I need it? Oh, there it is. So if I was to take 1/2 plus the sine of 6.28, now 6.28 being between 11 pi over 6 and 2 pi here, that is an 11 pi here over 6, I would get a positive number. I didn't have to take 6.28. I could have used 2 pi. I know that 2 pi isn't part of it, but I know the way my function is going to be behaving because of the cosine. So this turns out to be positive, and this is increasing here. Well, it goes from increasing to decreasing at 7 pi over 6. So I have a relative maximum at 7 pi over 6 of, and then I got to plug it in to figure it out, and it goes from decreasing to increasing. I have a relative minimum at 11 pi over 6, 11 pi over 6 of, and I got to figure that out. So if I got to go back to here and plug these values in. So here's where you guys sometimes go decimal crazy, but it's okay. You know, you're going to have pi, it's irrational and such. So it's 1/2 times 7 pi over 6. I'm just going to punch it out on my calculator here real quick. So 0.5 times 7 pi over 6. Let's see, minus the cosine of 7 pi over 6. All right? 2.698. So the 3 decimal places, we're going to go to 2.6986. We're going to go to 2.699. And for the minimum, I'm going to do the same thing, only this time I'm going to plug 11 pi over 6 in. So let's see here. 0.5 times 11 pi divided by 6. If I just knew how to type this stuff in a little faster. The cosine of 11 pi divided by 6 turns out to be 2.0137, so 2.014 to 3 decimal places. Now, those are not the extreme values. These are the extreme values. This is just where they occur at. All right, next guy up. Find the relative extrema of g of x equals x squared minus 4, all raised to the 2/3 power. So the first thing I need is the derivative. And let's see here. I do have a restricted, no, it's a cube root, so I'm okay. So it's all real numbers here. Let's see what we have. I'm going to get 2/3 times the quantity, x squared minus 1, excuse me, x squared minus 4 to the negative 1/3 times 2x. Don't forget the times 2x. That's the chain rule here, the generalized power rule. So 2x times 2/3, it's 4x over 3. I'm going to write this as 4x all over 3 times the cube root of x squared minus 4. Well, I got problems. Well, besides the obvious problems. This is going to be undefined at 2 and negative 2, because I'm going to get 0 in the denominator. So I have critical numbers at x equal plus or minus 2, and then if I set my derivative equal to 0, this is equal to 0 when the numerator is 0, and the numerator is 0 when x is 0. So I have 3 critical numbers. So I draw out my number line. This is for g prime, negative 2, 0, 2, and I test my intervals. take a value from here like negative 10. This is going to be negative on top, positive on the bottom. My derivative here, so that's negative. Take a number like negative 1. Negative on top. This is going to be negative on the bottom, so negative over negative is positive. Take positive 1. That'd be positive on top, negative on the bottom, so that's going to be negative. And take a number like 10. Positive on top, positive on the bottom, so that's positive all the way through. So this is decreasing, then it's increasing, then it's decreasing, then it's increasing. I have one relative max at 0. I have two relative mins. So I have relative maximum of at x equals 0. So at x equals 0, 0 squared minus 4 is negative 4 to the 2/3 is the cube root of 16. Whatever that is. That's 2 cube roots of 8. Excuse me, 2 cube roots of 2. Simplifying my radical. And then I have relative minimums of, let's see, here at x equal negative 2, and a relative minimum at x equal positive 2. So let's see, at negative 2, I get 0. At I get 0 both times. All right. Hopefully you can see that all right. It got a little messy there, hopefully, and then I've got it slanted here because of the way I write. Hopefully you can see that okay there. All right, so I took the derivative, I found my critical numbers, I broke up my number line for my derivative, and then I tested each of the subintervals, and based on that I determined increasing and decreasing, and then applied that theorem, the first derivative test for the increasing and decreasing, and then I can use this to determine my relative extrema. One more to go here. Find the relative extrema of the function h of x equals x to the 4th plus 1 all over x squared. So let's take a derivative. Now notice here, undefined at 0. So this would be, for all values h, the domain of h would be from negative infinity to 0 and from 0 to infinity. All right, so I got to remember that 0 is not part of my domain here. H prime of x would be, now that's going to be a quotient rule, so it's low d high minus high d low all over the square of what's below. So this is 4x to the 5th minus 2x to the 5th, I'm distributing here, minus 2x all over x to the 4th. So this is, let's see, let's bring it over here, 2x to the 5th minus 2x all over x to the 4th. So this is 2x to the 4th minus 2 all over x to the 3rd. Well, this is equal to 0 when the numerator is equal to 0. So you can divide through by 2. I get x to the 4th minus 1 is equal to 0. So that is x squared minus 1 times x squared plus 1. Oh, you probably can't see that anymore. X squared plus 1 equal to 0. So that's going to give me x equal plus or minus 1, and those are going to be imaginary, so that's no help there. So I have two critical numbers. But watch when I draw my number line out here. I'm going to draw my number line out here for h prime. I'm putting 0 in there. It's not a possible relative extrema because it's not part of my domain. Negative 1, positive 1. Now let's test those intervals. Take a number over here like negative 10. Where's my, there it is. This is the guy here. If I put negative 10 in here, that's going to be 20,000 minus 2 over negative 1,000. That's negative. If I take a number here like, let's say, negative 1/2. Ooh, this is going to be fun. Negative 1/2, that would be 1/16, 1/8 minus 2. That's negative on top. Negative 1/2 to the 3rd is negative. Negative over negative is positive. All right. Decreasing to increasing, I'm going to have a relative minimum. I take positive 1/2. Positive 1/2, That's going to be 1/16. 2 times 1/16 is 1/8 minus 2. It's negative on top. Positive on the bottom is negative. Take a number over here like 10. So I'm going to have positive over positive. So this is decreasing to increasing, so I'm going to have relative minimum here as well. I have two relative minimums. I am really interested all of a sudden in what my graph might look like. So I have relative minimums. I have at x equal -1. Let's go back to the original. That would be 2 over 1, which is 2. Relative minimum of 2 at x equal +1. Relative minimum also at 2. All right, well, I got to graph this thing. Let me get my calculator out. Let's see if this backs it up here a little bit. So this is x to the 4th. Let's see here. Oh, hang on. Let's try it. Would be nice if I plugged it in right. X to the 4th. What is that? +1 divided by, what is it? Divided by x squared. And let's see what the graph looks like here. Let's just start with a standard and see if this is going to show it here. Oh yeah, this shows it nicely. Look down here at these points here and here. Those are both, actually those are absolute extreme values. They're relative extreme values for sure, but they're absolute extreme values. And where does that occur at? It occurs at x equal -1, x equal +1, and it looks like a y value there of 2. So my answer matches up really nicely here with the graph to back it up. All right, so give these problems a good try. You're going to want to make sure that you know the first derivative test backward and forward. And in the next section, we're going to look at another test that will help us kind of determine the same thing called the second derivative test. But I don't want to give too much away yet. Make sure that you try these problems. Practice, practice, practice.